Well, in the last class we have seen what is meant by saying that a sequence is convergent or not convergent, and seen some methods of showing that a sequence either converges or diverges by directly by using definitions or by some other methods. And especially in showing the convergence we have seen that it is better to make use of several theorems about the sequences to show that some sequences are convergent. And in that we listed those theorems. For example, if you take two sequences, two convergent sequences, then their sum is also convergent sequence, product, etc. Okay, and one of the important aspects in that is that if the so called sandwich theorem, namely that if you take three sequences, let us say xn, yn and zn, and if xn is less than or equal to yn less than or equal to zn for each n, which we described by saying that yn is sandwiched between the two xn and zn, and if these two sequences xn and zn converge to the same limit, then yn also converges and it converges to that same common limit. Okay. And this is something which is used very often in proving that many well known sequences are convergent. Let us see some examples of this. Basically what we will do is that we shall make a list of some sequences whose convergence we shall be using very often. Okay. Let me just write it here. Okay. So let us say p bigger than 0, then limit n tends to infinity 1 by n to the power p is equal to 0, then again for p bigger than 0 limit n tends to infinity p to the power 1 by n is 1, and let us say similarly limit n tends to infinity n to the power 1 by n, that is also 1. By the way, this power 1 by n we have already defined. Okay, we have seen that given any positive number there and any natural number n, there exists a unique positive number x such that x to the power n is p. So p to the power 1 by n means that number. Okay. Then similarly we can say that limit as n tends to infinity, suppose here I take something like n to the power alpha divided by 1 plus p to the power n. Okay, here also I take p bigger than 0. Okay, then this limit is 0. Okay, alpha is also bigger than 0, and finally suppose you have mod x less than 1, then limit n tends to infinity x to the power n, that is also 0. Alright. We shall see proofs of some of these things. Okay, and others I shall leave as an exercise. Okay. Anyway, this we need not discuss it. We have shown already that 1 by n limit and how this Archimedean property or n is not bounded above, that comes into picture in showing this. Okay, and this 1 by n to the power p, you just multiply it sufficient number of times if p is an integer. Other cases also you can take care of it. Let us just look at this. Okay. Now p is bigger than 0. Okay, we will need to make if p is equal to 1, there is nothing to prove, right? This becomes a constant sequence. So we need to consider only the cases p bigger than 1 and 0 less than p less than 1, right? So let us just see the proof of this. Let us see the proof of the case when p is bigger than 1. Okay. P is equal to 1, the case is trivial. Okay, and other possibility is that 0 less than p less than 1, but you will see that if we prove this case and if you take 0 less than p less than 1, 1 by p will satisfy this. Okay, right, and if p to the power 1 by n, if the limit of that is 1, limit of, you can look at limit of 1 by p to the power n, that will also be 1. So the other case also can be taken care of. Okay, so it is enough to prove this. Okay, it is enough to prove this case. Okay, let us say that I will take this xn as p to the power 1 by n minus 1. Okay, alright. Is it clear that this is always bigger than or equal to 0? Okay, right. And suppose we show that xn tends to 0 as n goes to infinity, okay, then it will mean this, right? Okay, because the difference between this is xn. So if we show that xn, if the limit of xn is 0 as n goes to infinity, that will prove the required thing. Alright. Now I say that we are going to use sandwich theorem. So what I will do is that I shall construct a sequence which is bigger than or equal to this, let us say yn, and show that 0 less than or equal to xn less than or equal to yn for each n, and yn goes to 0. Okay. Okay. Now let us see how this can be done. Alright. Now this is same as saying that p is equal to 1 plus xn raised to n, right, 1 plus xn raised to n. Okay. Now this is same as 1 plus n xn plus, okay, there will be few more things, I do not bother about that. Okay. Okay. Is it clear that because xn is all non-negative, in fact positive, all the terms here are positive. So any term here is less than or equal to p. Okay. Any term here is less than or equal to p. Okay. So it follows from here. So I will say that okay, that is whatever is this part is any term or any 2 or 3 or any number of those terms. So I can say from here that xn is less than or equal to p minus 1 by n for all n. Okay. You can call this yn if you want. Okay. And this tends to 0 as n, that is clear. Okay. This tends to 0 as n tends to infinity. Okay. And so xn is bigger than or equal to 0 and xn is less than or equal to yn, and yn tends to 0. So you take the constant sequence 0 and this sequence, this given sequence xn is sandwiched between these two, so its limits must be 0, right. Okay. Fine. Alright. Let us look at this. See. Again there also it is similar. Okay. I will again consider, okay, instead of calling it, I will consider this xn as, or let us say yn as n to the power 1 by n minus 1. Okay. Now this is same as saying that n is equal, okay, it is clear that this is always bigger than or equal to 0, right. Okay. And again if I proceed in a similar way, I can say from here that this is same as saying that n is equal to 1 plus yn to the power n. Okay. Now suppose I do the same thing here also, I can say that this is same as 1 plus n by n etc. Okay. But you can see that if I again here every term is positive, so I can take any number of terms or group of terms and use this, but you can see that if I just stop here and proceed in this way, what I will get is yn is less than or equal to n minus 1 by n. Okay. And limit of that is not 0. Instead of p minus 1 by n, you will get n minus 1 by, and n minus 1 by n, the limit of that is 1. Okay. So you can't use sandwich theorem. Okay. Right. So what we will do is, okay, we will see whether we take one more term. Okay. So what is the next term here? 1 plus n by n, the next term will be n into n minus 1 by 2 into yn square. Okay. This is also less than or equal to this, right. This is also less than or equal to this. So what you get from this, n into n minus 1 by 2 yn square, that is less than or equal to n. Okay. Now that is same as saying that yn is less than or equal to square root of 2 by n minus 1, right. Okay. Because this term is less than or equal to n. Okay. This term is less than, okay. So from that you will get it yn is less than or equal to square root of 2 by n minus 1, and now this tends to 0. Okay. Now this tends to 0. So yn also must go to 0, and that is same as saying that the limit of n to the power 1 by n is 1. Okay. Alright. I shall leave the proof of this last two to you. Okay. This next one is again similar. Okay. Next one is again similar. There you will need more than this. Okay. Here we have stopped with the term yn square. Okay. There you will need some more terms. Okay. But again the idea is very similar. I suggest that you try to do these two things on your own. take it as an exercise, and you can see that once you do this D, E is straightforward, you can just take alpha is equal to 0 here, then that will give you E, okay, that will give you E, fine, okay. Then there is another technique in showing that the sequence, certain sequences are convergent, okay. Again you may be familiar with this, but let us again repeat that. To do this we will need a concept of what is called a monotonic sequence, monotonic sequence, okay. Let us just recall the definitions for a second. Suppose you are given a sequence xn, a sequence xn is said to be monotonically increasing well is already well known, when increasing if each succeeding term is bigger than or equal to the previous term, okay, monotonically increasing if we can say xn is less than or equal to xn plus 1 for all n, okay. And similarly you can define what is meant by monotonically decreasing, you can say it is decreasing, instead of this will be replaced by xn bigger than or equal to xn plus 1, okay. And what is meant by a monotonic sequence? Monotonic means it is increasing or decreasing, okay. Monotonic means it is increasing or decreasing, monotonically increasing or monotonically decreasing, that is monotonic sequence, alright. Then we come to again a very well known theorem in this. If a sequence is monotonically increasing and bounded above, then that converges, okay. And that is a very one of the well known techniques in showing that several sequences are convergent sequences, okay. So let us just recall that, let xn, yeah, by the way this is a standard notation to say that xn, you write this upward arrow, okay, that is a notation to say that xn is monotonically increasing, okay. Similarly the arrow pointing downwards for monotonically decreasing, okay. So I will just use this, okay, let xn be a monotonically increasing sequence, okay, and let xn be monotonically increasing and bounded above, okay, then xn converges. In fact we can say something more, okay, we can also say exactly what it converges to, okay. It converges to the least upper bound of this set, okay. It take set means take the range of the sequence, take its least upper bound, and then it converges, okay, to that, okay. We can say that limit of xn as n tends to infinity is nothing but this LUB, least upper bound of xn, or as you know it is already also called supremum of xn. Yeah, and by the way if a monotonically increasing sequence converges to a limit x, okay, then we simply denote it by this symbol, okay, right, that is xn is monotonically increasing and converging to x, okay, and in view of this theorem it also means that x is the LUB of that, okay, right. This is something which we should be using very often, okay. What is important to realize is that this theorem follows again because of the LUB action, okay, because it is a non-empty set, it is bounded above, so it has a least upper bound, and so the LUB axiom plays a very important role in this. Okay. So let us say that since Xn is bounded above, it has the least upper bound. Suppose I call it least upper bound x. Suppose I call it least upper bound x. Okay. Then how does one show that a sequence converges? Well, we have to say for every epsilon bigger than 0 there exists n0, etc. Okay. So let us take epsilon bigger than 0. Okay. Then we have seen already how does this epsilon and LUB comes into picture, that is if x is an least upper bound, it means that
take any epsilon x minus 7, there exists an element of a x such that which are
greater than
there exists element of x के greater than होचे m minus epsilon.
See, it is a least upper bound. Okay, x is a least upper bound, that means x plus epsilon is not an upper bound. Okay, if x plus epsilon is not an upper bound, what should happen?
x minus epsilon is
Sorry, x minus epsilon is not an upper bound. So what should happen? That there should exist some element xn which is bigger than x minus epsilon. So we can say there exists n0 in n such that x n0, this must be bigger than x minus epsilon. Right. Okay. All right. Now this is something we could have said about any bounded set for any sequence. Okay. But now in case of this sequence, we know that it is monotonically increasing. Okay. So if it is monotonically increasing, if you take, say for example, if you take n0 plus 1, it should be bigger than or equal to x n0, n0 plus 2 it should be bigger than x n0 plus 1. In other words, for any n bigger than or equal to n0, x n0 should be less than or equal to xn. In fact, that is something we can say about any monotonically increasing. Xn is less than or equal to xn plus 1, xn plus 1 will be less than or equal to xn plus 2, that will be less than or equal to xn plus 3, etc. So in general we can say that if you take two natural numbers n and m in n with n less than or equal to m, this will mean xn is less than or equal to xn for monotonically increasing sequence, and inequality will be reversed for monotonically decreasing sequences. Okay. So what we can say is that then for all n, so let us say that let n be bigger than or equal to n0. Okay. Then x minus epsilon, this is strictly less than x n0, this is less than or equal to xn. Okay. Okay. And we can always say that xn must be less than or equal to x because it is an upper bound. Okay. Okay. Xn is less than or equal to x. Okay. And in fact x will always be less than x plus epsilon. Okay. So x is less than x plus epsilon. Okay. So what did we show? That for every n bigger than or equal to n0, xn lies between x minus epsilon and x plus epsilon. Okay. That is the meaning that xn converges to x. Okay. Right. So so we have proved that every sequence which is monotonically increasing and bounded above converges. Not only that, we have also shown that it converges to its least upper bound. Okay. All right. In a similar way, we can show that every sequence which is monotonically decreasing and bounded below will also converge, and it will converge to its greatest lower bound. Okay. So instead of increasing, suppose you change this to decreasing, then xn, and in fact it should be bounded below. Okay. Suppose we make it bounded below. Okay. Then that sequence also converges, and it will not converge to LUB, but it will converge to GLB. Okay. And proving that is simple. Okay. Once you prove it something for an increasing, either you can imitate the proof in the same way, other possibility is that if xn is monotonically increasing or xn is monotonically decreasing, minus xn is increasing, right. If xn is monotonically decreasing, then minus xn is increasing. So use the theorem for increasing sequences, okay, and then get the required things. Anyway, that proof I shall not discuss here, that you can prove on your own, okay. Now this is a theorem which is quite useful in showing that the several well known sequences which we come across are convergent, and it will also be quite useful subsequently, okay, and also to say also to define something that we want to talk about little later. But before that, let me just take one or two well known examples. You also know that one of the ways of defining a sequence, because the sequence is a function from the set of all natural numbers, and the set of all natural numbers satisfies what we have called the principle of induction, okay, right. So for example, I can give the value of x1, okay, and then I can tell how to compute x2 from x1, x3 from x2, etc. okay. This is what is called defining the sequence inductively, okay, that is give the value of what is x1 and then say how xn plus 1 is computed from xn, then that defines all the numbers in the sequence, right. Again, this is just one possibility. I can also give the value of x1 and x2 and then say how to compute xn plus 2 from xn and xn plus 1, okay, right. That will also define the whole sequence, okay. So this is called defining the sequence inductively, okay. But once the sequence is defined inductively, then every property of the sequence also has to be checked by induction, okay, by mathematical induction. And one of the ways of showing that such sequences are convergent or divergent is that you show that the sequence is monotonically increasing or bounded above, or the other way, decreasing and bounded below, okay. Let us just take one example of that form. So define xn as follows. Define xn by let us say x1 is 1, okay, and xn plus 1 is equal to, let me say, half into xn plus 2 by xn, okay, for all n, okay, n equal to okay, alright. So when a sequence is defined in this form, the only way to discuss its convergence or divergence is that you have to see whether it is increasing and bounded, okay, alright. Let us first see whether it is increasing or decreasing, okay. That you can see because if you look at x2, it will be half into 1 plus 2, so it is bigger than, so if at all we hope to show anything, it has to be monotonically increasing, okay, alright. What about the boundedness? We can try to show that x1 is, see for example you can see that x1 and x2 both are less than or equal to 2, so we can say that we can attempt to show it is bounded above by 2. I mean if it fails we can choose some other number, but let us try with this, okay. So first of all x1 is 1, so obviously we can say that 1 less than or equal to x1 less than, in fact let us say we want to show this 1 less than or equal to xn less than or equal to 2 for all n, okay. Let us say when we want to show something we usually write that as a claim, okay. This is true for n equal to 1, okay, this is true for n is equal to 1, so assume that it is true for some value of n, okay. So assume true for some n in n, okay, and then with that we should try to show it is true for xn plus 1, okay, alright. Now since xn plus 1 also involves the reciprocals, let us write this inequality in terms of reciprocals also. See 1 less than or equal to xn less than or equal to 2, this also means 1 by 2 less than or equal to 1 by xn less than or equal to 1, right, okay, because this also may be needed in proving, okay, alright. So now look at xn plus 1, that is suppose this is true, we want to prove similar thing is true for xn plus 1, okay. Now xn plus 1 is equal to half into xn plus 2 by xn. Okay. Alright, so this is less than or equal to half into xn is less than or equal to 2, okay, xn is less than or equal to 2, and then plus 2 into 1 by xn is less than or equal to 1, right, 1 plus 2 into 1, okay, and so half into 4, so this is 2, so this part is fine. So xn plus 1 less than or equal to 2 is fine, okay. Can we also that xn plus 1 is bigger than or equal to 1? Okay, let us see how that follows. This is bigger than or equal to half into xn is bigger than or equal to 1 plus 2 into 1 by xn is bigger than half, 1 by xn is bigger than half, right, bigger than or equal to half. So this is half into 1 plus 1, so that is okay. Okay. So we have shown that if 1 less than or equal to xn is true for some value of n, that is also holds for xn plus 1, okay. So by induction it holds for all n, okay. So by induction it holds for all n, okay. Now what is the next thing that we need to show? We want to show that xn is monotonically increasing, okay. So next, okay, you can call this claim 1. So claim 2, xn is less than or equal to xn plus 1 for all n, and as you know in most of the induction proofs the case for n equal to 1 is trivial, right, okay. So what about n equal to 1? X1 is 1 and you can calculate whatever is x2, okay, and just check that it is bigger than or equal to 1, okay. So true for n equal to 1. Okay. Now let us see whether we can use this to show that okay, let us see now next what is it to show that xn is less than or equal to xn plus 1, what is it that we need to show? Xn plus 1, okay, let me just write what is that we need to show that xn plus 1 is half into xn plus 2 by xn. We want to show that this is bigger than or equal to xn, right, we want to say this is bigger than or equal to xn. So what does it mean? Is it same as saying that suppose I bring this 1 by 2, so that is 1 by xn is bigger than or equal to half xn, right, that is xn minus this half xn, right. So that is same as saying that we must show that xn square is less than or equal to 2, right, we should show that xn square is less than or equal to 2, okay, right. So suppose we had shown that here instead of 2, suppose I had taken root 2, okay, and tried to show that xn is less than or root 2, then this itself it would have been over here, okay, right, but obviously that cannot work, so again we will have to use the induction, okay. I think since this proof is fairly routine I will not go into this, okay, that is you assume that xn is less than or equal to xn plus 1 and show xn plus 1 is less than or equal to xn plus 2, okay, take this as an exercise, that is fairly routine, so I will not discuss it here, okay. The next question is, so suppose we prove these two things, it will mean that this sequence converges, okay, this sequence converges. Next question is if it converges what is its limit, okay, what is its limit, okay. Again you know the well known argument for this, if xn converges, suppose limit of xn is equal to L, suppose limit of xn as n tends to infinity is equal to L, okay. Then first of all it will be in that 1 less than or equal to L less than or equal to 2 because of what we have proved here, okay, right. First of all 1 less than or equal to L less than or equal to 2, okay. But there is one more important thing, okay, limit of xn plus 1 as n goes to infinity, that is also L, okay, right, that is limit of also limit of xn plus 1 as n tends to infinity, that is also L, okay. But xn plus 1 is half into xn plus 2 by xn, right. Now limit, so limit of this we can also convert limit of this in different way. So limit of this is also nothing but half into L plus 2 by L, okay, right. And so what we will get is that this is L is same as half into L plus 2 by L, okay. And if you simplify this you will get half L is same as 1 by L, and you will get this as L square is equal to 2, L square is equal to 2, okay, right. So L is equal to, that will give L is equal to plus or minus root 2, okay? L is equal to plus or minus root 2, but you have this, okay, so it cannot be minus root 2. So limit of this sequence, limit of xn as n tends to infinity, that is nothing but root 2, okay. This is one of the well known techniques in finding the limits of many sequences which are defined in this fashion. Let me again tell you that here I have given the value of x1 and we have defined xn plus 1 in terms of xn. It is also possible to give x1 and x2 and define xn plus 1 in terms of xn and xn minus 1, that is taking the two previous things, okay, and similarly 3 terms etc, okay. These are nothing but the small modifications of this same idea, okay. Now before going to the next concepts, let us also complete a discussion of this well known sequence. Xn is 1 plus 1 by n raised to n, xn is 1 plus 1 by n raised to n, okay, a familiar sequence to you, okay. Again here also we can show that this sequence is monotonically increasing and bounded above, okay. Let us just quickly look at what are the steps in showing that, okay. So suppose you expand this by using binomial theorem, then this will be 1 plus it is next term is n into 1 by n, so that is also 1 plus n into n minus 1 into n minus 1 by 2 into 1 plus into 1 by n square etc. The next term will be n into n minus 1 into n minus 2 divided by factorial 3 into 1 by n cube etc, okay. Now what we can see from here is that this will be 1 plus 1, this will be 1 plus, see we will rewrite this term in a slightly different manner. I will divide by n square to these terms n into n minus 1, okay, right. So this can be written as 1 into 1 minus 1 by n into this 1 by factorial 2, then the next coefficient will be 1 into 1 minus 1 by n into 1 minus 2 by n into 1 by factorial 3 etc. This is just basically rearranging and to see that it is convenient to see, okay, right, okay. Now if I take xn plus 1, okay, what is going to happen here? You are going to get 1 by n plus 1 into n plus 1, okay. So this is going to be changed to 1 by n plus 1, 2 by n plus 1 etc etc, okay. Is it clear that that is bigger than or equal to this? 1 by n plus 1 will be smaller than 1 by, and but you are subtracting, okay. So the corresponding term in this will be bigger than or equal to corresponding term here, okay, and plus you will have one extra term because it is the power is n plus 1, okay. So xn plus 1 bigger than or equal to xn for all n, that is clear, okay. In fact that is the reason for writing it in this fashion, okay, alright. Is it clear? Okay. One more thing, okay, each of this xn is see, remember each of these terms are non-negative, okay, each of these terms are non-negative. So we can also and so everything here is this 1 plus 1 is 2, okay. So we can always say that 2 is less than or equal to xn always, okay, right, and also xn is less than or equal to, each of this term is less than or equal to 1, okay, 1 minus etc, whatever is occurring here that is less than or equal to 1, okay. So xn is less than or equal to, we can say that 1 plus 1 plus 1 by factorial 2 plus 1 by factorial 3 etc plus 1 by factorial n, okay. And you can say one more thing here, that is, okay, for example if you look at this 1 by factorial 3, okay, see 1 by factorial 3, it is nothing but 1 by 1 into 2 into 3, so this is less than or equal to 1 by 2 square, okay, because this 3 I am replacing by 2. Similarly 1 by factorial 4, this 3 4 etc, all of them I can replace by 2 and I can say that is less than or equal to 1 by 2 cube etc, okay. So in general I can say that this is less than or equal to 1 plus 1 plus 1 by 2 plus 1 by 2 square etc plus 1 by 2 to the power n minus 1, okay, right. And then you know that familiar argument, this is a geometric progression, so the sum of this will be, sum of this part will be less than or equal to 2, okay, okay, because sum of this part will be nothing but 1 minus half to the, okay, let us write it, this is same as 1 plus 1 minus half to the power n divided by 1 minus half, okay, right, or which is same as saying that this is 1 plus 2 into 1 minus half to the power n, okay. And obviously this 1 minus anything is less than or equal to 1, so this is less than or equal to 1 plus 2, so this is less than or equal to 3, okay. Anyway, so what did we prove? That for each xn 2 less than or equal to xn less than or equal to 3 for all n, and xn is less than or equal to xn plus 1 for all, okay, right. So we have proved that its sequence is prototypically increasing and bounded above. Of course we also proved it is bounded below, but that is not relevant, okay, okay. So this sequence xn converges, this sequence xn converges, and you all know that its limit is called the number e, okay, its limit is denoted by the number e, okay. So e is limit n tends to infinity. In fact there are various ways of defining this number e, this is one of those ways, 1 plus 1 by n raised to n, okay, alright. And because of this we can say that this number e lies between 2 and 3, okay. So 2 less than or equal to e less than or equal to 3, and if you want to get an approximate value of e, you take some large value of n and compute the corresponding fraction here and you will get the value of e, approximate value of e. Okay. Now let us proceed to the concepts. Is it clear? So far whatever we have done, we have shown that every sequence which is prototypically increasing and bounded above converges, similarly for decreasing sequences, and we have seen how to make use of these theorems to show the convergence of some of the well known sequences, okay. Now let us just take a sequence which is just bounded, okay, let us say that xn is just a bounded sequence, okay. What does this mean? It means it is a sequence which is bounded above and bounded below, right, the sequence is bounded above and bounded below. Since the sequence is bounded above, it will have a least upper bound, since it is bounded below it will have a greatest lower bound. Let us use some notations for this, okay. So let us say that let me say let alpha is LUB of xn and let us say beta be GLB of xn. Okay. So first of all it will mean that beta is less than or equal to xn less than or equal to alpha for all n. Okay. Just to keep track of what is happening, let us keep some example in mind. Okay. Okay, I will write it here. Consider this sequence 1 minus 1 1 minus 1 etc. How to describe this sequence? I can write xn is equal to minus 1 to the power n plus 1, right. If I take minus 1 to the power n, first will be minus 1, okay. So minus 1 to the power n plus 1, okay, alright. So what are the alphas and betas here? What? Alpha, so in this case alpha will be 1, beta is minus 1, okay, alpha is 1, beta is minus 1. Of course this is a trivial example, but it just helps to know what is going on here, okay. Now next what I want to do is the following, okay. For example, now if I take any, okay, let us suppose I take I will define alpha 1 as LUB of this whole sequence x1 x2 etc, and similarly beta 1 as GLB of x1 x2 etc. Of course then you will see that this is nothing new, because then alpha 1 is same as alpha and beta 1 is same as beta, but still I am using this notation because I want to define a few things subsequently for which this is more consistent, okay. Next what I will do is that I will drop this first term x1 from the sequence, okay, and then take the LUB of the remaining part of the sequence, okay, right, and call that alpha 2, okay, call that alpha 2, that is instead of taking x1 x2 let me take the sequence x2 x3 etc, okay, and take the LUB of that, okay, and call that number alpha 2, okay, and similarly beta 2 is GLB of x2 etc, okay, and then proceed in this manner, okay. So next I will take alpha 3 as the LUB of the sequence x3 x4 etc, okay, right. So in general I will say that you take alpha k as LUB of xk plus 1 etc, and similarly beta k GLB of xk etc. Okay. I think once you understood what are these etc, let us now write in a concise notation, okay. I will say that I will write it here. What is alpha k? Alpha k is least upper bound of xn for n bigger than or equal to k, right, okay, and similarly beta k is GLB of xn for n bigger than or equal to k. That is, you are just taking the part of the sequence xk plus 1 etc, and is it obviously clear that all of these are also bounded above and bounded below, right, because it is a part of the original sequence that you start with, okay, and so each of this alpha k must be less than or equal to alpha, each of this beta k also must be less than or equal to beta, and what is the relationship between beta k and alpha k? Beta k is less than or equal to alpha, right, beta k is less than or equal to alpha k for all k, and each of this alpha k is less than or equal to alpha, and each of this beta k is bigger than or equal to beta, okay, alright, okay, alright. Now let us come to a very important question, okay. What is the relationship between alpha k and alpha k plus 1?
alpha k is greater than or equal to alpha k plus 1.
right, alpha k is bigger than or equal to alpha. Why?
Because this is the supreme.
So you are taking supremum over a smaller set, right? Okay, you are taking the least upper bound of a smaller set. Okay, so that should be less than. Okay? It may be equal to, but it should be in general. So alpha k plus 1 is bigger than or equal to. Okay, right? So this alpha k is a, remember this alpha k itself is also alpha k and beta k are also sequences. Okay, so this is true for all k. So what follows? Alpha k is monotonically decreasing. Alpha k is monotonically decreasing. Okay, is it bound? Now once a sequence is monotonically decreasing, to know whether it is convergent or not, what we should know? Whether it is bounded below. Okay, is that the case? Okay, because each alpha k is bigger than or equal to beta k, and beta k is less than or equal to beta. So this beta is a lower bound for all of these alpha k's. Okay, similarly it is a lower bound for all of these beta k's also, but that is okay. Okay, so alpha k's and beta k's, those are sequences which they are also bounded above and as well as below, but what is additional thing here is that alpha k is monotonically decreasing. Similarly you can say that beta k is monotonically increasing. Okay, so that is beta k is less than or equal to beta k plus 1 for all k, because in a smaller set the upper bound should increase. Okay, lower bound should increase. Okay, in the smaller set lower bound should increase. Okay, so the given sequence xn may or may not be broader monotonic. Okay, it may or may not be monotonically increasing or decreasing, but this new sequence alpha k and beta k, those are monotonically, alpha k is decreasing, beta k is increasing. So these sequences will always have limit. Okay, these sequences will always have limit. Okay, and what will be the limit? Its limit will be nothing but the, for example, limit of the alpha k will be nothing but the okay, of course that limit may or may not be same as alpha, or that limit may or may not be same as beta, that limit may be different. Okay, so that limit has a special name. Okay, it is called, for example, this limit of this alpha k, this limit will always exist, this limit will always exist. Okay, right, this is called, so let us just note this. Okay, this alpha k and beta k are convergent sequences always. Of course we cannot say that alpha k converges to alpha, because alpha k is a monotonically decreasing sequence. Okay, and so we know that a monotonically decreasing sequence will converge to its greatest lower bound. Okay, and that may not be alpha, in fact in general it will not be. Okay, in general it will not be alpha. Okay, so so that may be some different number. Okay, that may be some different number. So that number is called limit superior of this sequence xn. Okay, that number is called limit superior. So limit of alpha k as k tends to infinity, that is called limit superior of xn. Okay, and similarly limit of beta k as k tends to infinity, this is called limit inferior. Of x. Okay, all right, but we can notice one more thing here. Okay, this is a monotonically decreasing sequence. Okay, so it must converge to its infimum. Okay, it must converge to its greatest lower bound, so it must converge to its infimum. So what we can say is that this limit superior, what we have called here, okay, let me write it here. Okay, so limit superior, as this is denoted like this, limit superior denoted like this, limit superior as of xn as n tends to infinity, limit superior of xn as n tends to infinity. Okay, but this is nothing but, according to us, limit as k tends to infinity of alpha k, right, limit. But what is alpha k? Let us look at alpha k is nothing but least upper bound of xn. Okay, so we can say that alpha k is nothing but least upper bound is same as supremum, right, least upper bound. So this is supremum and bigger than or equal to k xn, okay, right. And since this alpha k is a decreasing sequence, its limit is nothing but infimum of that sequence. So I can say that this is nothing but infimum k bigger than or equal to, let me simply say infimum over k supremum over n bigger than or equal to k xn, okay. In the same way we can say that limit inferior of xn, okay, let me just write it and then we will stop with that. Similarly, limit inferior of xn as n tends to infinity, there this inferior and infimum and supremum will be interchanged, okay, because beta k's are not supremum but they are infimums, okay. So this is supremum over k, infimum over n bigger than or equal to k xn. Since beta k is a increasing sequence, it will converge to its supremum, and beta k itself is infimum for each k, right. So that will be the limit inferior of xn, okay. So the given sequence xn may or may not be convergent. Once the sequence is bounded, it may or may not be convergent, but it will always have limit inferior and limit superior, okay. And what are the corresponding quantities for this sequence? For this sequence it is 1 and minus 1, okay, 1 and minus 1, okay. Alright, we will stop with that for today. We will see how to use these concepts of limit inferior and limit superior subsequently.